This lesson is about polyatomic ions. It's built on concepts that we learned previously about monoatomic ions and about how to predict the shape of simple molecules. If you don't remember those things, please go back and review first. We're talking about polyatomic ions. Monoatomic ions, to review, are atoms that either have gained electrons, so they become negative by gaining electrons, or they've lost electrons and become positive. Ions that have extra electrons are negative, and they're called anions. Okay? Anions are negative. Polyatomic or monoatomic ions. If they have extra electrons, they're negative. They're called anions. If they have they've lost electrons, they don't have enough electrons to balance out the number of protons, that's called a cation. They're positive. Okay? Polyatomic ions. These are covalently bonded groups of atoms. So they're covalently bonded together. It's like molecules. They're covalently bonded together. Okay? But with an unequal number of protons and electrons. And that's why they're charged, either positively or negatively. They're going to have an uneven number of protons and electrons. Okay? So we're going to deal with some very, very simple stuff to introduce you to this whole concept. We're going to start with water. Pretty simple stuff, okay? Just to remind you about how we get the Lewis dot formula for water, let's start with the electron dot formulas. Here's the electron dot formula for hydrogen. It's the valence electrons that we use to make the dots. Just the valence electrons, those in the highest energy level for that particular atom. Well, hydrogen only has one energy level. It only has one electron. It just has one dot. Oxygen has two primary electron energy levels. In the highest primary energy level, it has two s electrons and four p electrons. Those are the valence level electrons. There's a total of 6 valence electrons in oxygen. You can look at where it is on the periodic table, figure out the s and p sublevel regions, and figure that out. It's not that hard. But anyway, 1, 2, 3, 4 electrons, one on each of the 4 sides. Pair up on 2 sides to get the total of 6 electrons that oxygen needs. Then we have a second hydrogen, okay, and then they share electrons here and here, okay, in order to give hydrogen 2 electrons, so it has a full valence level, and oxygen gets 8 electrons. There's the octet rule. Okay, 8 electrons fills up its valence level, making both the hydrogen and the oxygen more stable. So when we write the Lewis dot formula, then we squeeze the electrons that are shared in between the atoms and include the lone pairs on there. Okay, lone pair electrons that remain there. Now, turns out that in any sample of water, there's no such thing as pure water, because no matter how pure you make it, how hard you work to get all the impurities out, there's also a certain tiny number of water molecules that break up. Okay, it's called autoionization. The term we're going to look at here is autoionization. Ionization because it creates ions, auto because it happens automatically. So what happens is this water molecule breaks up. The hydrogen, which had 1 electron when it was just a hydrogen atom, leaves without its electron. Okay? This hydrogen is going to leave without that electron. It's going to leave that electron on the remainder of the water molecule, which is not going to be a water molecule anymore. So it's just a hydrogen with no electron. Well, it has no electron it only has a proton. What is its charge? Positive. Okay? So we could call this a hydrogen atom, or we could call it a proton, because it is both. Okay? All right, so if hydrogen leaves without its electron, then what's going to be left is everything else. So the other part that's there, once the hydrogen separates, is this. So the oxygen atom has 8 protons. The hydrogen atom has 1 proton. Okay? So for the oxygen, we have 8 protons. For the hydrogen, we have 1 proton. So we've got a total of 9 protons in this structure over here. Okay? We had 8 electrons on the oxygen to begin with. We only showed the 6 because we're only looking at the valence level when we're writing the electron dot notation. The hydrogen originally had 1 electron, so it had 9 electrons, right? But this right here got an extra electron from that hydrogen, remember? So not only do we have those 9 electrons, we'll have 1 more electron. So this structure right here has 10 electrons and 9 protons, which means it has a charge. An uneven number of electrons and protons means it has a charge. What's its charge? Negative. And since that a negative actually applies to the whole thing, so we did this when we're looking at monoatomic ions. If you remember when we were doing Lewis dots with monoatomic ions, and we moved the electrons around, we put extra electrons on a single atom, we used a bracket like that. We're doing the same thing here to show that negative charge applies to the whole structure. Okay? This is also an ion because it's a charged particle, but this time it's a covalently bonded group of atoms with an unequal number of protons and electrons. That's a polyatomic ion. It has a special name. Okay? Let's see. This is OH negative, and it's called hydroxide. One of the molecules we've worked with a lot in here as far as learning shapes and things and doing electron dot formulas and then coming up with Lewis formulas was ammonia. This is ammonia. But if you go to the department store or the grocery store and you buy a bottle of ammonia, that's not really what you have. If you open the top and smell it, that's what you're smelling, but it's not what's in the bottle. Okay? We're going to look at what you actually have in the bottle. Okay? So, ammonia. When we do the electron dot formulas and do the sharing arrangement, this is electron dot formula, sharing arrangement becomes the molecule. I'm just going to give you the molecule down here. You need to be able to do the electron dot formula sharing arrangement and find the molecule in Lewis dot form. Okay? But I'm just going to show you the Lewis dot form here. So this is ammonia in the Lewis dot form, or the Lewis dot formula for ammonia, you could say. Okay? Now this is neutrally charged. I have an equal number of protons and electrons in this molecule. That's why we went through that whole sharing arrangement, so we didn't lose any electrons. We had the same number of electrons that we started with, same number of protons we started with, we have at the end. Okay? So this is a neutral. This has a neutral charge, no charge. Okay, it's neutral, no charge. But I'm going to put it in water. And in water, some of the molecules of water have split up into these things, right? So in water, we also have some of these. So this comes from water. When I put it in water, there's some of those in there. We're going to put this in the proximity to that. They're close by. Now, the reason that hydrogen, the atom, bonded with the oxygen to start with is because it wanted 2 electrons. Well, this hydrogen, or this proton, this hydrogen ion or proton, still wants 2 electrons. And it can get those 2 electrons from the ammonia. It doesn't take it away from them. It's going to share electrons to give it 2 electrons. Okay? And it's going to do so by going over here and covalently bonding with that pair of electrons. So it's attracted to and then shares electrons. Attracted to and shares the pair of electrons. Okay? Let's look at what it looks like now, using Lewis dots. So we had the ammonia molecule. There's the lone pair. And that pair of electrons on the top is going to share, or the nitrogen is going to share that pair of electrons on the top with this hydrogen ion. As a result, this extra proton is put on this molecule that had a neutral charge. Well, that means you've got one more proton than all the electrons. Okay? Which means this new molecule has a positive charge. We don't really call it a molecule anymore. We call it a polyatomic ion. It's a covalently bonded group of atoms with an uneven or unequal number of protons and electrons. In this case, we have more protons than electrons. In this case up here with the hydroxide, we had more electrons than protons. Okay? So this has a special name. It's called ammonium. And generally when we write the formula for ammonium, we write it as NH4+. Just to kind of quickly tie into stuff we learned about previously. We're writing the formula, if you will, for isotopes. We put the mass up here on the upper left, the number of protons lower left. The charge position is reserved. This spot up here in the upper right is reserved for charges. The lower right, this number is reserved for telling us how many atoms there are bonded together. Okay? NH4 means there's 1 nitrogen and 4 hydrogens. You with me? Got that? Let's take it a step further. Here's our NH4. And we used up the hydrogen ion we made from water. There's also this OH over here, which we call hydroxide. So we're in the South. Everybody in the South knows what I mean when I say, looky here. Okay? Positive charged particle, negatively charged particle. What's going to happen there? Huh? They can cancel each other out. They're also attracted to each other by opposite charges. So theoretically, at least, we can make this ionic compound. No charge, because we've neutralized the charges by putting together two oppositely charged ions. Okay? And it's not made of monoatomic ions. We were working with monoatomic ions earlier. Now we have 2 polyatomic ions put together into a neutral compound. Okay? So this is named ammonium hydroxide. You don't change the names of the polyatomic ions when you put them in a formula. They are what they are. Okay? Ammonium hydroxide. Now, I kind of worded that carefully a while ago because even though I said it theoretically forms that, in the real world, let's say you were to make some ammonium hydroxide and evaporate all the water, you wouldn't get crystals of ammonium hydroxide. It just doesn't work that way. I don't know if theoretically you can make it happen by adjusting all the parameters, environment, things like that, and make crystals of ammonium hydroxide, but you don't get it when. Basically what happens is the whole reaction we've described here goes back the opposite way. The ammonia evaporates out with the water, and you don't get any ammonium hydroxide. Okay? Got all that? But since we're here, and since in tomorrow's test we've got to know about molecular shapes, let's look at the shape of ammonia and ammonium. Okay? Let's remind ourselves about molecular shapes using those. Okay? So here's ammonium, all right? And going back to ammonium, if we're to put this together, we could go and use the electron dot formulas. Well, I should put a hydrogen there. Let's just take that off there and start with 4 hydrogens and a nitrogen. Nitrogen has 5 electrons. Hydrogens have 1 electron. But remember, one of those, the hydrogen we got previously, this hydrogen here didn't have any electrons on it. So this is actually H plus with no electrons on it. It's actually a proton. Got that? So we could put this together if we're going to use electron dot formulas, then do the sharing arrangement. Share the electrons. That brings nitrogen up to the 8 electrons it wants. Each of the hydrogens has 2 electrons it wants. Oh, except for this one. So this just simply joins up there, and we still get ammonium, don't we? In the electron dot formula we looked at earlier. But that extra proton means this whole structure has a positive charge. Alrighty then. Another southernism. If this is the shape, or this is the Lewis dot formula for ammonium, how do we find the molecular shape of this polyatomic ion? What's the first step? What do we call the first step, the first drawing we do when we're figuring out molecular shapes? Well, not electron model, but you're getting close. It is electron in there, yeah. Not modified. It's just electron pair shape or electron dot shape. Okay? I have 1 set of electrons on this side. 1 set here, 1 set here, 1 set here. 4 sets of electrons around the central atom. What 3-dimensional geometric shape do you make when you have 4 sets of electrons around a central atom? What? It's not a T. Tetrahedral. Okay? So that means I have to have the nitrogen in the middle. Now, in high school chemistry, we don't look at what's happening with every single atom in a structure. We're only looking at 1 atom at a time. So we're trying to keep it pretty simple and look at 1 atom in high school chemistry, okay? So the tetrahedral means I have 1 arm, is the way we usually draw it anyway. 1 arm going up, 1 coming out at 109.5 degrees from that. You need to know that angle. 1 of them has to come out toward you, kind of off the paper, all right? And 1 goes back behind the paper, and all of these have angles of 109.5 degrees from all the other arms, or all the other angles, okay? And so we're going to put just the sets of electrons on there. So each of these arms has 2 electrons on it. And that is called a tetrahedral. Okay? We could call it electron dot shape or electron pair shape. Okay? Tetrahedral describes the geometry. Electron dot shape describes the type of drawing I'm doing, the type of three-dimensional structure I'm building. Okay? After we have the tetrahedral electron dot shape, what is the next thing we do? Well, it could be modified, but what do we do to get the modified electron pair shape? What do we do? Replace any sets of electrons that are shared with the atoms with which they are shared. So in this case, all 4 sets are shared with hydrogens. So the next drawing won't have any sets of electrons. It'll have just hydrogens on the end of those arms. So what's the geometry of this then? No? I'm looking for the geometry name, like tetrahedral. It's still tetrahedral. No, it's not a trick question. You need to know this stuff. But this is, since there are no lone pairs left, once you've gotten rid of all the lone pairs, it's not modified electron pair shape, it's the molecular shape. Once you don't have any lone pairs left on the structure, then you have a molecular shape. Okay, but it is positively charged, so I still need to put this in a bracket and put a positive charge outside to show that. Okay? So we figured out excuse me, that this polyatomic ion has a tetrahedral molecular shape. That makes sense? And you got to do this on the test tomorrow. So you need to know it. Well, let's go back and look at ammonia then. Can you find the molecular shape using this process for ammonia? Find the molecular shape for the ammonia molecule using the same step-by-step process. All right, let's take a look. If we're using the electron dots, the electron dot formulas and finding the sharing arrangement, ammonia started out with, or nitrogen started out with 5 electron dots. Hydrogens started out with 1. Share electrons such that hydrogen ends up with 2 electrons and nitrogen ends up with 8. So the Lewis dot formula then is this, where you squeeze the electrons between the atoms in the formula, and then we still have a set of 4 sets of electrons around the atom we're most interested in here, and that's going to start out being a tetrahedral, just as we had previously. So this is a what?
Okay, wait, so even if it's just 3 hydrogens, you draw the 4.
You have to start out with a 4. Exactly right. So this is a tetrahedral, because this shape is determined by the sets of electrons around the central atom. Whether they're shared or lone pairs, it doesn't matter. The one at the top here is called a lone pair. All of these that are shared between the hydrogens, we call them a shared pair. Okay? So this is a tetrahedral electron dot or electron pair shape. All right. The next step then is to replace all the sets of electrons that are shared with the atoms they're shared with. So I'm going to share this pair here. I'm going to share this pair here. I'm going to share the pair back here in the back. And I'm going to leave this lone pair up here unshared. So this is still a tetrahedral.
Can it be any of the 4 that you
Yes. You can be any of the 4. And we call this is where we call it the modified electron pair shape. Okay? Then we have one more step to do. So when we're doing this shape up here, we stop after just 2 steps with three-dimensional drawings. In this case, we're going to need 3 steps to get to the final molecular shape. The final molecular shape then removes the lone pair, but it keeps all the other angles exactly the same. The only way we know what the final shape is going to be is if we remember the shape or space taken up by this lone pair up here. So now that's not tetrahedral anymore. This is then called trigonal pyramidal. Okay, it looks like if you sort of joined up all the angles at the bottom, it looks like a pyramid. And this is not an electron pair shape. This is a molecular shape. All right. Okay, we did all of these molecular shapes and things near the beginning of the unit, so make sure you go back and review all those so that you know what the different shapes are. Okay, there's linear, there is bent, there's trigonal planar. Okay, you need to know about all those shapes. If I have this shape, this is called linear. If I have this shape, this is called tetrahedral. Can we have a little less noise and stuff out here for a minute, okay? If we have this shape, I'm making this one trigonal pyramidal. Let's see here. If we had so bent, then is this. Okay, that's bent. And trigonal planar this is trigonal planar. All right. In addition to knowing what the three-dimensional or geometry names are, you also have to know what the type of drawing or what the composition of the structure is. So you have to know if it's a electron pair or electron dot shape. You have to know if it's a modified electron pair or electron dot shape. You have to know if it's a molecular shape. Okay. So when you name those different structures, you have to have both. If it's three-dimensional, you have to have both the geometry and the type of drawing. Does that make sense? So this is geometry tetrahedral, type of drawing electron pair shape. This is geometry trigonal pyramidal, type of drawing molecular shape.